Welcome back, everybody. This is our sixth session in JEE Mains previous year questions for chapter Wave Optics of class 12. Before this video, we have made 5 videos in this series, and all of those videos are available on our YouTube channel's playlist section. We have also started similar series for NEET. So if some of your friends are preparing for NEET, then they can also watch those videos, and you can also get some additional practice from the NEET. If you find these videos useful, then do press the like button, share them, and subscribe to our channel. Also, if you like to support us financially, you can scan any of these QR codes in front of your screen and donate us with whatever amount you want. With this, let's start today's video. In the previous one, we covered up to around 60. This was, I think, one of the last one. Today, we will start with this. That is 59th. Let me adjust pen thickness. And let's start. So here we have unpolarized light of intensity I passes through an ideal polarizer A. Another identical polarizer B is placed behind A. The intensity of light beyond B is found to be I by 2. Now another identical polarizer C is placed between A and B. The intensity now found to be I by 8. The angle between A and C is. So it is mentioned that initially, suppose this is our polarizer A, and here uh, we have incident light I, that is unpolarized light. Now when a unpolarized light incident on a polarizer at any angle, the output is always I by 2. And what is happening that there is another polarizer B, and even after passing through the polarizer B, the light is I by 2. So between for polarizer B, we can write that IB will be equal to I incident on the B into cos square of phi. Now output of B, that is IB, that is I by 2. Input of B, that is again I by 2, and into cos square phi. From this we can write that phi is going to be 0 degree, means angle between A and B is 0 degree. So both A and B are practically they are parallel. So from that, now we have introduced another polarizer C at some angle. So let me change this color first. I think it is well fine. So here, suppose that was initially our A, this was B, and now we added a polarizer C. Now this polarizer is at angle theta with respect to axis of A, and with respect to B it will be again theta because A and B are parallel. So here we have light incident I. After passing through A it will be I by 2. After passing through C it will be I by 2 into cos square of theta using law of molars. And after passing through B, again between angle between C and B is theta, so it will be I by 2 cos square of theta into cos square of theta, and this is given equal to I by 8. So from this we can say cos raised to power 4 is equal to 1 by 4, and taking solving this, taking quadrant root, so we will get cos theta is equal to 1 by root 2, and from that theta will be 45 degree. That is option C for us. So option C is right answer here. Moving ahead. So here we have light of wavelength falls normally on a slit of width 22 into 10 to the power minus 5 centimeters. So slit width is given. Angular position of the second minima from the central maxima will be. Now we know that for second minima, in case of diffraction, condition is reversed. For diffraction we have a sine theta, that is the path difference, is equal to n lambda. This is condition for minima, not maxima. Now we want for second minima, so we will get a sine theta is equal to 2 lambda, and from this sine of theta is equal to 2 lambda by a, that will be 2 into 550 into 10 raised to power minus 9 divided by A, that is 22 into 10 raised to power minus 5, and that is in centimeters, so 10 raised to power minus 2 additional, that will be in meters. So this will be 50, this will be 2, this get cancelled, and we have 5 into 10 raised to power minus 8 and into 10 raised to power plus 7. This will give us 0.5. So sin theta is 0.5 over half, and theta will be 30 degree, and that will be pi by 6 radian. That is option D for us. In the next one, unpolarized light of intensity I is incident on a system of two polarizer A followed by B. The intensity of the emergent light is I by 2. If the third polarizer C is between A and B, the intensity reduces to 1 I by 3. The angle between A and C is theta. Then we have to find out theta. So this is a similar type of question which we done already, and I think it was the 59th. So in the initial setup, this is A, and here we have unpolarized light of intensity I. So output will be I by 2 for unpolarized light. And now there is B polarizer, and intensity is output intensity is again I by 2, means angle between A and B is 0, or A and B are basically parallel to each other. Now what happens? We add another polarizer C between them. So this is A, this is B, and suppose we added a polarizer C such that it makes an angle theta with respect to A, and as A is parallel to B, so the angle with B, the angle C makes with B is again going to be theta. So here we have incident intensity I, then after A it will be I by 2, then after C it will be I by 2 cos square of theta, and after B it will be I by 2 cos 4 theta. Now this should be equal to I by 3. So I by 2 cos 4 theta is equal to I by 3. Now I get cancelled from this, and we will get cos of theta is equal to 2 by 3 raised to power 1 by 4, and that is option A for us. Now moving to the next one. A plane polarized light is incident on a polarizer with its path axis making angle theta with x-axis as shown in the figure. At four different values of theta, 8, 38, 188, 280, the observed intensities are same. The angle between the direction of the polarizer and x. So here what we can do, we can assume we have to assume that our direction is suppose that one, this direction is our x-axis, and here, oh sorry, the x-axis is already given. This is our x-axis. So, and the angle is theta, which is made by the polarizer. So suppose this is the polarizer here. Now we don't know the angle of light here, so we assume that suppose this is the angle of light. This is light, and that light is making angle phi with x-axis. So basically we will calculate theta plus phi here. So when light passes through the polarizer, it will become suppose initial intensity is I, then after passing through the polarizer, because between light and polarizer total angle is theta plus phi, so it will become I of cos square theta plus phi. Now it is mentioned that at 4 value of theta the intensity is same, so we can write that I of cos square 8 plus phi will be equal to I times of cos square 38 plus phi, and that should be equal to I cos square 188 plus phi, and that should be equal to I cos square of 218 plus phi. Now I get cancelled on each side, here, and we know cos of we know that cos of 180 plus theta is basically minus of cos theta. And now if we square, then we can write that cos square of 180 plus theta, that will be basically theta here, that will be basically cos square theta. So here this 188 plus 5 will be equal to again 8 plus 5, and this 218 plus 5 will be again equal to 38 plus 5. So basically we have a relation that cos square of 8 plus 5 is equal to cos square of 38 plus 5. Now the only value which is going to satisfy this, that will be 203. So option will be, answer will be 203. Out of all given values, only the only answer which is going to satisfy this will be 203. So option A will be the right answer here. Now in the next one, observer is moving with half the speed of light towards the stationary microwave source emitting waves at frequency 10 gigahertz. What is the frequency of microwave measured by the observer? So here we will use relativistic Doppler effects, and here we will have relation that frequency that is observed will be equal to the actual frequency or f source into under root 1 plus v by c divided by 1 minus v by c. So that will be 10, and answer will be in gigahertz. Now speed of the source is half of the speed of light, so we will get 1 plus c by 2 divided by c by 1 minus c by 2 divided by c, and from this we will get 10 root 3, that will be 17.3 gigahertz. That is option A. In the next one, a single slit of width 0.1 millimeter is illuminated by a parallel beam of light of 6000 angstrom, and diffraction bands are observed 0.5 meter on the slit, 5 meter from the slit. The distance of the third dark band from the central bright band will be. Now here we have only single slits. Basically it means there is a case of diffraction, and for diffraction we know that a sine theta is equal to n lambda. This is the condition for minima. So here we can write that for the third minima we will have a sine theta is equal to 3 lambda, and from this sine of theta will be equal to 3 lambda by a. Now suppose this is our setup, this is screen, and here we are getting third minima. So if I draw a line here, then this distance will be the x, and this will be approximately equal to the screen distance d. So if this angle is theta, then here we can write that theta is equal to x by d if theta is small, and if theta is small, then sine of theta can be written as theta. So from this we can write that theta is 3 lambda by a, and from here theta is x by d, comparing both of these. So x by d is equal to 3 lambda by a, and from this x is equal to 3 lambda d by a. So basically 3 times the width, and substituting values we will get 3 into 6 into 6 into 10 raised to power minus 6 multiply capital D, that is 0.5 divided by a, that is 0.1 10 raised to power minus 3. Solving this we will get 90 into 10 raised to power minus 3. I think there should be, it should be the 9 into 10 to the power minus 3. Let me check it again. So here it should be 10 raised to the power minus 7, because it was 6000. So 10 raised to the power 3 into 10 raised to the power minus 7. So this will be this is 7, this will be 4, so this will be 4, and this will be 9 into 10 to the power minus 3, that will be 9 mm. So option B here. In the next one, a single slit of width b is illuminated by a coherent monochromatic source of wavelength lambda. For if the second and the fourth minima of the diffraction pattern at a distance of 1 meter from the slit are 3 cm and 6 cm respectively from the central maximum, what is the width of central maximum and distance between first minima on the either side of the central maximum? Now we have just solved here. In the previous one, in case of diffraction, what we can write here, from this expression we can write that theta will be approximately equal to n lambda by a, and here we have theta is equal to x by d, so both of these are equal. So from that, n lambda by a is equal to x by d, or suppose that is for xn, distance for the nth minima. So xn comes out to be n lambda d by a. This is for the diffraction, and we can use it here. So here xn will be equal to n lambda d by a. So here we have distances for the second minima we have 3 centimeter distance, and for the fourth minima we have 6 centimeter. So x2 is 3 centimeter, 3 into 10 to the power minus 2, and x4 is 6 into 10 to the power minus 2. Now we can here we see that if we write it like this, so this will be 3 into 10 to the power minus 2 is equal to 2 lambda d by a. Now we know that this 2 lambda d by a is equal to, this is the width of, central maximum. This is the formula for basically width of the central maximum, and that is equal to 3 centimeter. And we have been asked that width of the central maximum what is, so it will be again that will be the same value, that is 3 centimeter. So in the next one, we have a box of pinhole camera of length L has a hole of radius A. It is assumed that when the hole is illuminated by the parallel beam of light lambda, the spread of the spot obtained on the opposite wall of the camera is sum of geometric spread and spread due to diffraction. The spot would have its minimum size, say B minimum value. So we have to find out that what will be the minimum value of B. So to solve this, let us first make the diagram. So suppose this is our slit and this is our scale. Now spread will consist of two parts, that is spread due to diffraction and geometrical spread. Now geometrical spread means that light is traveling in a straight line. So if light is traveling in straight line, means it will look like this. That from the, suppose there is a light source and light is traveling in straight line like this. So this will be the equal to geometric spread, and spread due to diffraction will be that light bends around the corner, so it will look like this. That spread due to diffraction. Suppose this is the spread due to diffraction, and this will be the angle theta. Now we are only considering here spread up to first minima. We are not considering it up to infinite. We are only considering first minima. So, and we know that we just solved that for the minima, for the nth minima, our distance, this distance xn will be equal to n lambda d by the slit width, that is a. So for the first minima, this will be x1, that will be lambda d by a, and this geometric spread will be equal to slit width, so that will be basically equal to a, and here slit width, okay, yeah, slit width is a here, I think. So our total separation, or our this total distance, one correction here, that this slit has a radius of a. means this this hole this slit is in the part of it in the form of a circle, and this circle has a radius a, so slit width will be actually 2a, so that's why we have to add 2a here. So this will be 2a. So this total distance will be, we can say this total distance b will be equal to 2a plus 2 times lambda t by a on the upper side and on the lower side. So we can take 2 common, and this will be a plus lambda d by a. Now we have to minimize the size. So to minimize the size, what we will take derivative of this with respect to a. So db by da will be equal to twice as it is. This will be 1 minus lambda d by a square, and to find the value of a further, so we will equate equal to 0. So from that we will get 1 is equal to lambda d by a square, and from this a is equal to under root lambda d. Now d is equal to, going to their length l. This is given equal to l, so this will be a will become a is equal to under root lambda l. So if a is under root lambda l here, if we match it, then option a can be right answer and option d can be a right answer. Now let us find out the value of b. So value of b will be, that will be twice under root lambda l plus we have lambda times d, and that d is equal to l. So lambda l divided by a, that is under root lambda l. So this will give us 4 under root lambda l. Yes, 4 under root lambda l. I think there is a mistake. So this 4 should be outside. So from that we can say option A is going to the right answer, going to be the right answer. Now the next one, two stars are 10 light years away from the Earth. They are seen through a telescope of objective diameter 30 centimeter. The wavelength of the light is 600 nanometer. To see the stars just resolved by a telescope, minimum distance between them should be. So we have to find out their minimum distance. Now we know that, as here it is mentioned, that we have to use our eye in combination with telescope. So the angular width or the minimum angle which our eye can resolve, that is 1 by 60 degree. This is the angle uh, that should be this is the angular angle which our eye can resolve properly. If angles made by the object or made by the distant object on the eye is smaller than this one, then we will not able to see the that object clearly, or those two objects distinguished or separately. So first of all, let's convert into radian. So this will be equal to pi by 180 into 1 by 60 radian. Now angular width for the telescope will be equal to lambda by t. So this lambda by t should be lesser than pi by 180 into 60, and if we take inverse, then d by lambda is greater than 180 into 60 by pi, and from this if we calculate d, then d will be greater than or equal to 180 into 60 into lambda by pi. When we substitute value of lambda and pi, we will get d greater than 2 into 10 raised to power minus 3. Oh, sorry, we made a mistake here. I took value from the different questions. Okay, let me clear this one first. Let's start from the beginning. So here we have the diameter and we have the distance. So we know theta for the telescope will be 1.22 lambda times t. So that will be 1.22 lambda is 600 nanometer, 10 is power minus 9. divided by the diameter, that is 30 centimeters, so 30 into 10 raised to power minus 2. So this is the minimum value of theta which can be resolved by the telescope, that will be 24.4 into 10 raised to power minus 7 radian. Now theta is equal to going to be arc by radius. So theta we have already calculated, so that is 24.4 times power minus 7, and that is equal to the arc, means distance between stars divided by the distance from which we are viewing, that is 10 light years. So that will be 10 into 9.46 into 10 raised to power 15 meters. So when we solve this, we will get distance between stars, that will be 9.46 into 10 raised to power 16 into 24.4 10 raised to power minus 7, and that will be approximately 2.4 into 10 raised to power 11 meters, or that will be 2.4 into 10 raised to power 8 kilometers. And if we write it only in the form of order, so that will be 10 raised to power 8 kilometers. Now in the next one, assuming human people to have a radius of 0.25 centimeter and a comfortable viewing distance of 25 centimeter, minimum separation between the two objects that human eye can resolve at a 500 nanometer wavelength is. So we know that resolving power of a lens is equal to 1.22 lambda divided by the d, and d is the diameter, and that will be equal to twice the radius, so 2 times r. Now this resolving power should be equal to this separation between the distance, separation between the objects by the distance of the object. So from this we can write that x is d into 1.22 lambda divided by 2r, and that will be equal to the value of d here is equal to 25 into 10 raised to power minus 2 into 1.22 into lambda, that is 500 10 raised to power minus 9 by twice of 0.25 10 raised to power minus 2, and we will solve this. We will get 15 micrometer, and that is nearest to the option D at 30 micrometer. So option D will be the right answer. Now unpolarized light of intensity I node is incident on a surface of a block of glass at Brewster angle in the case which of the following is true. So at Brewster angle we know that both reflected and transmitted light will be plane polarized. Now suppose this is the surface upon which light will get reflected. So suppose this is the incident light, this is the reflected light, and this is the transmitted light. So this is reflected and this is transmitted. Now when light gets reflected, only electrical part is getting reflected, not the magnetic part. And here also, here both electric and magnetic parts are getting transmitted. So means this reflected part will going to have lesser intensity, because this is there is only electric part, not magnetic one. So from that we can say that reflected light is completely polarized with intensity less than I node by 2. Transmitted light is also completely polarized and its intensity will be greater than I node by 2. And here in case of intensity is equal to I node by 2 be given. So both option B and C and D will be wrong. Only option A will be the right answer. Now two beam A and B of a plane polarized light with mutually perpendicular planes of polarization are seen through a polaroid from the position when a beam A has maximum intensity and B has zero intensity. The rotation of polaroid through 30 angle makes two beams appear equally bright. If the initial intensity of the beam I and B respectively, then IA by IB we have to find out. So it is mentioned that at angle 30 degree, both of the beam appears equally bright, and initially one has the maximum intensity and other has the zero intensity. So from that we can say that for the one if one light is polarized along y axis, then another light is polarized along x axis, because both of these are mutually perpendicular. Now we take a polarizer, and that polarizer makes, suppose, 30-degree angle with one light. Then it has to make 60-degree angle with another one, and as it is mentioned that intensities are equal, so we can say IA of cos square 30, that should be equal to IP cos square 60. So from this, IA by IP will be equal to 1 by 3, and that is option D here. Moving to the next one. The diameter of the objective lens of the microscope makes an angle beta at the focus of the microscope. Further, medium between the object and the lens is an oil of refractive index and the resolving power of the microscope. So we know that resolving power of microscope is 2 mu sine theta by lambda, and this can be written as 2 times n, where n is the refractive index, into angle, sine of angle, that is beta, by lambda. So resolving power will increase if this term n sine beta increases. So it will increase with increasing value of n sine 2 beta, because if beta is increasing, 2 beta is increasing, means beta will be also increasing. So option C we can say is going to be the only right answer here. So with this we end this video here. Hopefully whatever we covered today is helpful to you. Again, if you have any doubts or suggestion, you can put them in comment section, and also you can like and subscribe to our channel, and if you like to donate something, you can scan these QR codes. With this, again, thanks for watching, and we will meet in next video.